very much. And thanks very much for the invitation. So I want to talk about an old question about random integer polynomials and their Galois groups. Namely, if you pick a random integer polynomial of a fixed degree, how often does it happen that it has the full Galois group Sn? Or rather, how often does it happen that it doesn't have the full Galois group Sn? This question goes back to Hilbert. So the question is, more precisely, you let En of h denote the number of monic integer polynomials. So let's say f of x equals x to the n plus a1 x to the n minus 1 plus dot 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 plus an, degree n, where each coefficient ai is at most h in absolute value. So it said the Galois group is not Sn. Okay, so all monic integer polynomials whose coefficients are bounded by h in absolute value. So we want to know the number of them that don't have Galois group Sn. So if you think about it, there are clearly at least h to the n minus 1, right, on the order of h to the n minus 1 such polynomials, because if you let the final coefficient an be equal to 0, then clearly that doesn't have Galois group Sn because it's reducible. So yeah, just setting an equals 0, you can see that there are at least h to the n minus 1 that won't have the full Galois group Sn. And in 1936, van der Waerden made this tantalizing conjecture that h to the n minus 1 should also be the correct upper bound for the number of such polynomials that don't have Galois group Sn. So in other words, setting an equals 0 already produces the correct order of magnitude of polynomials that don't have Galois group Sn, and that should actually be the correct order of magnitude of the number of polynomials that don't have Galois group Sn. So in other words, if you pick a random such polynomial of height h, we're expecting that 1 over h of them won't have Galois group Sn, and the rest will have Galois group Sn. So that's van der Waerden's conjecture. And the conjecture has been known previously for degrees n at most 4, due to work of van der Waerden himself, in the case n equals 3, and then Chow and Dietmann in the case n equals 4, fairly recently. So that's the conjecture I want to talk about today. Is there any question about the statement? So we're just looking at all monic integer polynomials, coefficient height at most h. We want to know how many of them have Galois group that's not Sn. We expect at most on the order of h to the n minus 1. The total number of polynomials is h to the n, right? Or 2 to the n times h to the n, approximately, right? But, the correct order of magnitude for those that don't have Galois group Sn should be on the order of h to the n minus 1. So 1 over h to the n. Okay, so that's the conjecture of van der Waerden, 1936. And of course, Hilbert addressed this question. That's his famous Hilbert irreducibility. Hilbert irreducibility says that if you pick a random integer polynomial of height most h, that it should be 100% probability as h tends to infinity, the density should approach 100%, that they have Galois group Sn. So in other words, En of h should be little o of h to the n. That's Hilbert irreducibility. And so if you pick a random polynomial, the probability that it doesn't have Galois group Sn should be 0. So van der Waerden was asking basically for a quantitative form of Hilbert irreducibility. He wants to know that if you pick a random polynomial, how often does it happen? Not just that it's probability 0, but what is the order of magnitude? And in 1936, van der Waerden proved the first power saving in the statement of Hilbert by showing that En of h is big O of h to the n minus something small, but it's positive. But that positive thing tends to 0, but at least it's always positive for any particular n. So that was the first power saving off of the exponent n. If you just keep the exponent n there, that's the total number of such polynomials. And so van der Waerden is saying that there's a slight power saving for those that don't have Galois group Sn. And successive improvements to van der Waerden's bound were given by Knobloch in 1956. Improved another saving to alpha n that decreases quickly. But the key thing about Noblex bound is that the thing that he's taking off, the exponent he's taking off of n is independent of h. So van der Waerden's improvement depended on h. Noblex has a power statement that does not have. The real breakthrough in this area was by Gallagher, who invented this large sieve in order to address this problem. The large sieve, of course, has had applications everywhere since, but using the large sieve that he invented for this purpose, Gallagher was able to get a power saving off of n that's actually a fixed constant off of n that doesn't depend on n, namely 1/2. So he proved that E n of h is the most big O of h to the n minus 1/2. So this exponent is halfway between what we expect and the total. So total is h to the n. We expect h to the n minus 1. So this exponent is sort of halfway to the correct answer. The correct answer. That was using the large sieve, and with a more refined large sieve in Dietmann in 2010, I refined this to E n of h equals big O of h to the n minus 1/2. There's a lot of work to remove that epsilon. That was the contribution of Dietmann. It's larger sieve. So these were all these results were using sieve methods. And then a more algebraic method was introduced by Dietmann. One thing that's very cool about this problem is that many different methods have been used to attack it. Very analytic ones early on, and then more algebraic ones more recently. So Dietmann in 2010 proved using resolving polynomials and the determinant method, Bombier and Pila, that E n of h is the most big O of h to the n minus 2 plus square root of 2. So which you can see is a little bit smaller than n minus 1/2. And then most recently in 2021, there was a group at AIM that had a further improvement using the Selberg sieve as a large sieve. They showed E n of h is basically at most big O of h to the n minus 2/3. So the exponent has now sort of made its way 2/3 from the total to what's expected. That's using the Selberg sieve. Using the Selberg sieve kind of as a large sieve rather than its usual as a smaller sieve. So yeah, just looking at all this, it's very cool to see how many different techniques have been thrown at it over the years. And so what I want to do today is actually prove van der Waerden's conjecture for all degrees n in full. So I want to show that E n of h is actually big O of h to the n minus 1. That's conjectured by van der Waerden. And more generally, if you take any permutation group G in Sn on n letters, we can let nn of G comma h. We can introduce the Galois group G in there, right? So we can use that to denote the number of monic integer polynomials with coefficient bound at most h, coefficient height at most h, such that the Galois group is isomorphic to G. G being some permutation group on n letters, and we can ask, what are the asymptotics of that? Then the theorem we're proving, van der Waerden's conjecture, amounts to proving that nn of G comma h is big O of h to the n minus 1 for all permutation groups G contained in Sn. And then we can ask, well, can we get better bounds for other G? And the techniques I described today actually really take into account the structure of G, and the bounds depend on G, but they're all at most n minus 1. But the method I described today gives the best known bounds nn of G comma h for various individual groups G. But for today, I just want to concentrate on proving E n of h is the most big O of h to the n minus 1 in full. I'll point out in places where you could use the structure of G to do even better for individual groups G. Okay, so we'll go ahead and prove E n of h is at most big O of h to the n minus 1.
Sorry, does that HTM minus 1 come entirely from things with a linear factor, or are there other?
There are others.
Well,
so
like,
I see. You mean the total count?
If I were to exclude, if I excluded everything with a linear factor, would it?
I think it would. I think it would drop.
Okay.
But the proof I give today doesn't prove that. Okay. But expect it. Expect that. Okay, so we'll divide it. We'll divide the set of possible groups G into various categories. First, they're the intransitive groups G. So the fact that Nn of G comma H is big O of H to the n minus 1 for intransitive groups G, in other words, polynomials that factor, that was already shown by van der Waerden, using the fact that polynomials having such Galois groups are exactly those that factor over Q. So we want to show that the number of such monic polynomials with height at most H that factor is the most big O of H to the n minus 1. In that case, it's relatively easy and was already handled in the original paper by van der Waerden when he made this conjecture. And in fact, an exact asymptotic of the form, an exact asymptotic for the number of reducible such polynomials of coefficient height at most H was given by Chow in the 90s. So he actually computes an explicit constant Cn such that the order of such, the number of such polynomials, reducible polynomials, is Cn H to the n minus 1. So the reducible case was already known by van der Waerden, and we even know exact asymptotics. So that takes care of the intransitive because that's just counting reducible polynomials. Reducible polynomials you can just count by counting the factors and multiply them. Just count the little number of coefficients for the factors that you could have in these groups. It's down and actually work out an exact asymptotic. And then in case of imprimitive groups G, Dietmann has given excellent bounds. So Dietmann showed in the case of imprimitive Galois groups G. So just like intransitive groups G correspond to polynomials that are reducible, imprimitive groups G correspond to polynomials whose Galois groups, well, they're exactly those that correspond to number fields of degree n having a non-trivial subfield. That's what it means for. So if you have an imprimitive Galois group G, then that means that the degree n field, right inside Sn, that means that the degree n field has a subfield, non-trivial subfield. So you can count polynomials of degree n that give you imprimitive groups by sort of counting those polynomials that cut out a field that has a subfield. And so you can do that by summing over the subfields, and that gives you a saving. And that's what Dietmann does. So Dietmann proves that if G in Sn is transitive but imprimitive, in case you're not familiar with an imprimitive group in terms of group theory, just means that G is imprimitive, acting on n letters if it preserves some non-trivial partition of 1 through n. That's equivalent to saying in terms of Galois theory that there's a non-trivial subfield. And Dietmann proved that G in Sn is transitive but imprimitive. Then the total number of such polynomials of height at most H that have an imprimitive Galois group is at most big O of H to the n over 2 plus 2.
Sorry, maybe I didn't parse that. Can you give an example of something that's transitive but imprimitive? Or how can something be both?
Oh, so D4 is the smallest example. So D4, if you have.
So if it preserves a partition, then it will not map things out of that partition into other things?
That's right, yeah. So it'll preserve that partition. So for example, D4 acts on a square. Then if you look at the pair of diagonals, so 1, 3, and 2, 4, okay, that partition is preserved by the action of D4. The diagonals always stay on the diagonals. So that's an example of an imprimitive group. And so therefore, if you have a D4 quartic field, there is a non-trivial quadratic subfield. So for that case, you can count by the subfields, and that's what Dietmann does, and that's why Dietmann gets a substantial saving for those polynomials that have a non-trivial, like cut out a field that has a non-trivial subfield, namely big O of H to the n over 2 plus 2. So what this slide means is that we can concentrate on the Galois groups G that inside Sn that are primitive, that don't preserve any non-trivial partition of 1 through n. So because of these results for intransitive groups and imprimitive groups, we can concentrate on the case of primitive permutation groups G inside Sn, those that don't preserve any non-trivial partition. So that's what we'll do. So it'll suffice to show that Nn of G comma H is big O of H to the n minus 1 for primitive permutation groups G. Okay, so then we can do a little group theory and try to understand, well, which are the primitive Galois groups that are not Sn? Okay, because we're interested in Galois groups that are not Sn, and we want them to be primitive. And there's this old result that goes back to Jordan, group theory, that if G in Sn is a primitive permutation group on n letters, and if it contains a transposition, then G actually has to be Sn. So the only primitive permutation groups in Sn that have a transposition is Sn. And it's not so this theorem goes back to 1873, I think. From a modern point of view, it's not too hard to see. We can define an equivalence relation. So suppose you have a primitive permutation group that contains a transposition. You can define an equivalence relation on 1 through n by saying that I and j are equivalent if the transposition I, j, right, I comma j, is there in the group. That's clearly an equivalence relation on 1 through n. And it has to be that partition of 1 through n with that equivalence relation has to be preserved by G. And yeah, so because it's primitive, that equivalence relation has to be the trivial one. And so we have all, if it has one transposition, it has to have all. And then so therefore it's Sn. So Sn is a primitive permutation group with a transposition, and it's Sn. Okay, so a corollary of that, just from the algebraic number theory point of view, is that if f is an integer polynomial of degree n, and we make the field q bracket x modulo f of x, call that case of f. If the Galois group of f is not Sn and it's primitive, then the discriminant of kf has to be squareful. Squareful meaning that every prime dividing the discriminant has to actually divide it to order at least 2. So the reason for that is if you have a degree n extension and its corresponding Galois group, its associated Galois group in Sn is primitive, and it's not Sn, then we know it doesn't contain any transpositions, right? And so that means all elements are either double transpositions or 3 cycles, or even have even more cycles in the cycle structure, bigger cycles. And so if you take any prime, right, and you look at its tame inertia, it will be generated by something, and that something cannot be a transposition. So the p-adic valuation of the discriminant there has to be these 2. Because you never have tame inertia generated by transposition, because there are no transpositions. So what that's saying is that that means we're counting polynomials as Galois groups. We're counting polynomials whose number fields always have discriminant that's squareful, and that's already a huge restriction. So that's what we want to take advantage of. That we've reduced to the case of primitive Galois groups that are not Sn, and those always correspond to number fields having discriminant that's at least a square or higher powers, right, at each prime. So that's what we want to take advantage of. We're only counting those f's, that's the q bracket f mod f of x has discriminant that's squareful. Okay, so this primitivity assumption and the assumption that it's not Sn leads to the fact that the discriminant is always squareful of the corresponding number. Okay, so another way to see this is that KF cannot have simple ramification. It's always going to be more complicated ramification, and so the discriminant valuation will always be more than 1. Okay, so that's the group theory preliminary. We need to prove the theorem. So we're first going to prove the weak version of the conjecture, which is that En of h is big O of h to the n minus 1 plus epsilon. Be off by an epsilon factor. Then if there's time, I'll talk about how to get rid of the epsilon. Getting rid of the epsilon is just as hard as the rest of the proof. So I thought maybe I'll concentrate first on n minus 1 plus epsilon. So to accomplish this, we're going to divide the set of irreducible monic integer polynomials with coefficient height at most h, and whose Galois group is not Sn, into three subsets. Okay, so let again KF be the field cut out by F, Q bracket X modulo F of X. And we're going to divide the set that we're trying to count, the set counted by En of H, into three subsets. Okay, so case one is going to be where the product C of the ramified primes and KF is at most H, but the discriminant, the absolute value, I should put absolute value, the absolute value of the discriminant of KF is at least H squared. So the product of the ramified primes is at most H, but the discriminant is a little bit bigger than we might expect, right? It's bigger than H squared. Remember the product of the ramified primes, if that's H, then the discriminant has to be at least the square of that, right? Because it's square fold. But if it's more than square fold, then the discriminant can become bigger than H squared. Right? That's the first case. The second case is going to be where the discriminant is at most H squared. Right? And then there's just one case remaining, which is that the product of the ramified primes is greater than H. So these three cases clearly cover all possibilities. So we just have to estimate each one of these. Right? So the first case is C is less than H, but D is bigger than H squared. The second case is where the discriminant of KF is less than or equal to H squared. And the last case is where C is bigger than H. Those three cases cover all possibilities for C and D. Right? C is the product of ramified primes. D is the discriminant of the degree n field associated with F. And these are the ranges of C and D where different techniques apply in order to prove this diagram. Okay, so the first case is going to be where C is at most H, the product of ramified primes is at most H, but the discriminant is at least H squared. That's what each of these in turn. So this is the first case, C is less than or equal to H. C is the product of ramified primes in KF, and D is at least H squared. The discriminant. That's the first case we consider. So given such a K that satisfies this property that its product of ramified primes is at most H, but its discriminant is at least H squared, the polynomials F such that KF is isomorphic to K have to satisfy congruence conditions that have density basically 1 over D, right? Because the discriminant of KF is D. So the probability that a random polynomial will have discriminant of a multiple of D, you can work out the density, it's going to be at least big O of something that's small in D divided by D. So for example, the probability that a polynomial has discriminant a multiple of P is 1 over P. Same way, if it's the probability that a random polynomial has discriminant multiple of P squared, you expect it to be 1 over P squared, but it's actually 2 over P squared. Work that out. But anyway, some constant times. In general, is that if you're going to ask for a polynomial to have discriminant valuation K, then you expect the probability to be a big O of something constant. You expect it to be most constant divided by P, because you have to be multiple P. So just the discriminant is a random number. The probability that it's going to be multiple P is going to be about 1 over D. And in fact, it's a little bit bigger. Something that's D to the epsilon divided by D.
That's a congruence condition modulo power of C.
That's right. Yeah. Yeah.
When you say probability, you mean like for H much bigger than that power, like let's say a little bigger.
Yeah. Yeah. But you can actually you can pick up because the discriminant, it's a discriminant of a field that's tamely ramified at P, say, right? Then you can pick up whether P ramifies a certain way by just looking at how the polynomial factors might be. So once P is past n, it's really just a congruence condition modulo C. You can pick that up. Right, if you know the splitting type of K, KF, then that corresponds to how F factors mod C. And if the prime is tamely ramified, then you can pick up the discriminant valuation just by understanding how P factors, how F factors mod. So it really is modulo C up to finite many times. That might be, well, It's just about the same. Okay, so polynomials abscess of k if isomorphic k have to satisfy congruence conditions, basically modulo c, and have density about big O of something small over d, one over d. And so the number of such f can be counted directly within the box where all the AIs are at most h in size. You can count it directly in that box, the side length h, because the congruence conditions are modulo c, and c is less than the size of the box. So you can just count how many things are in there, because modulus is smaller than the side length of the box. And so we immediately get the estimate big O of h to the n divided by d times s d to the epsilon for the number of such f. And so if we now sum this h to the n times d to the epsilon over d over all square full d bigger than h squared, that gives the desired estimate big O of h to the n minus 1 plus epsilon. Right? Because if we sum over all d at least h squared of big O of h to the n times the density of those things that are discriminating multiple of d, which is r to the omega d over d. Sum that over all d bigger than h squared that are square full, then that, because these d's are at most are always at least squares, or maybe have higher powers than them, the sum converges. It's exactly what we want. Big O of h to the n minus 1 plus epsilon. Okay, so this was the case where we could just impose congruence conditions modulo c. The condition c less than or equal to h is there because we can just count directly inside this box. Because you can count, obviously, modulo c inside a box whose side length is more than c. Okay, so that's the first case, c less than or equal to h. We impose c less than or equal to h because we can count directly inside the box, modulo c, because of the box size of this h. And we impose d bigger than h squared because the sum then converges to the right number.
So there's no 1 plus in this estimate on the number of guys in the box that line the set mod c. Like you have h to n times something. I'm just asking, why is there no kind of 1 there? Like how do you, like if the discriminant's bigger than h to n or something?
Yeah, there's no 1 because the modulus is smaller than the side length. If it was, if we were imposing conditions mod c and h was a lot smaller than c, then we'd get plus 1. But since we have this big box and our modulus is smaller than the size of the box, you're just sort of counting inside that box of size c. You can cover that. You can cover boxes of size c with your box of size h. And just count within each one the exact number.
Yeah, sorry. Thank you.
So that's the case c less than or equal to h and d greater than h squared. So now we'll go to the case where the discriminant d is less than or equal to h squared. First we had d bigger than h squared in this case, and now we're going to look at the case where d is less than or equal to h squared. In other words, the field cut out by the polynomial has small discriminant d less than or equal to h squared. Okay, so we consider those f, for which the absolute discriminant d of kf, q bracket x mod f, is at most h squared. So in this case, what we can do is we can actually just count in terms of the number fields, because we're saying that the discriminant of kf is at most h squared. There are not so many such number fields because we're bounding the discriminant. So the number of number fields k equals kf of degree n, and absolute discriminant of most h squared by a general result of Schmidt. That's at most, you take the discriminant h squared and you raise it to the n plus 2 over 4, n to the degree. That's the result of Schmidt, that you have at most that many number fields having discriminant at most is. Yeah, so if you take h squared and raise it to the n plus 2 over 4, that gives you bound on the total number of number fields of degree n that have discriminant at most h squared. That's big O of h to the n plus 2 over 2. And Schmidt's results has been improved spectacularly in recent years. First by Ellenberg and Benketish, who do way better than this. But in fact, Schmidt's bound suffices for our purposes, and it has the advantage that it works in small degrees as well. Whereas more recent results of Ellenberg and Benketish, Savigny's, most recently Lemke, Oliver, and Thorne, they've had successively better bounds for high degree. That Schmidt's bound works in all degrees, so we'll just use that. That's all we need. But just to point out, you do a lot better using more recent results. Okay, it just fits bounds enough. We're already at big O h to the n plus 2 over 2. This is how many number fields have of degree n that have discriminant at most 8 squared. And now we want to ask how many polynomials can come up from just that set of number fields. How many polynomials are there that cut out one of these number fields that have discriminant at most d squared? By results of Lemke, Oliver, and Thorne, each such number field k can arise for at most big O of h to the log h to the n minus 1 such polynomials. And that's not too hard to see kind of intuitively if you have a number field that has discriminant at most. Let's say you have a number field and you want to know how many polynomials give that number field that have coefficient bounds at most h. Well, you can just look at the last coefficient. Right? That's already saying that you're counting the number of elements that have norm at most h inside your number field up to the actual units, and that's really h to the 1 plus epsilon. That's basically what this bound is. Okay, that's the result. You can Lemke, Oliver, and Thorne that each number field arises gives a polynomial in not too many ways. Not too many polynomials cut out the same number field. Okay, so we had a bound on the number of number fields that are at most discriminant 8 squared, and then we have a bound of how many polynomials can cut out that same number field. And so if you just multiply those two bounds, so this is the total number of number fields discriminant most 8 squared, and how often each one can give you a polynomial whose coefficient bounds at most h. Multiply these two, you can see that that's at most big O of h to the n minus 1 once n is at least 7. And for small n, we know exact asymptotic results for quadratic, cubic, vertic, and quintic fields. And if you plug in those bounds for the number of number fields of degree at most 5, you get big O of h to the n minus 1 when n is less than or equal to 5 as well. N equals 6 if you plug in, you'll notice that you just miss. That's 6 plus 2 over 2, that's 4, h to the 4 times h to the 5. So you get the h to the n minus 1 plus epsilon here. But luckily, Lemke, Oliver, and Thorne prove a little bit of an improvement over h to the 1 plus epsilon. They're able to divide by a small power of discriminant in their results. And so that's enough to give you a power statement, even in the case n equals 6. They just barely get under the h to the n minus 1 you want. And it's actually better than the h to the n minus 1 for all n as a result of this tiny factor. You get a power statement for everything off of h to the n minus 1 actually. Okay, so that's case 2. And so the final case that remains is the case where the product of the ramified primes is bigger than h. And that is, of course, the hardest case. Because, well, if you want to just impose congruence conditions mod C, it's not so easy because the size of your box, the side length is smaller than C. So this is in some sense the part of the argument, so the hardest case. So finally, we consider those f where the product of the ramified primes q bracket x mod f of x is greater than h. So okay, so let's fix such an f. And for every prime p that divides C, you see that the polynomial f has either a double root mod p, right? That has a pair of double roots mod p or a triple root mod p. Right? Because we know that kf has square-fold discriminant. So any prime, if you look at the polynomial mod p, it'll have to have either a triple root or a pair of double roots, right? In order for the discriminant of kf to be square-fold at p. You'll never just have a single double root mod p. Right? Once you have a double root mod p, you have at least 2 double roots or a triple root in order to make the discriminant square-fold. So that's what we're excluding here. This is what followed from Jordan's lemma about primitive groups before. So the point about this is that the fact that f has either 2 double roots or a single triple root mod p, because that's the condition, if you change f by a multiple of p, that fact doesn't change about it. Right? So discriminant of f is a multiple of p squared, and it's a multiple of p squared for what I call mod p reasons. That if you change f by a multiple of p, it's still going to have discriminant of multiple of p squared, because it will still have either a pair of double roots or a triple root mod p. So changing f by multiple of p doesn't change the fact that p squared divides the discriminant. Okay, so not only is the discriminant of f a multiple of p squared, but f plus any multiple of p will also have discriminant of multiple of p squared. So it has discriminant of multiple of p squared in a very strong way. You can change it by any multiple of p, and it continues to have discriminant of multiple of p squared. And so we say that discriminant of f is a multiple of p squared for mod p reasons. And so here's a proposition about polynomials that take a value that's a multiple of p squared for mod p reasons. So just a general proposition: if you have a multivariate integer polynomial h of x1 through xn, and suppose that there's something you can plug, some integers you can plug in there to get a multiple of p squared. Say h of c1 through cn is a multiple of p squared. And suppose that if you change what you're plugging in by a multiple of p, it still stays a multiple of p squared, no matter what multiple of p you translate that. So suppose h of c1 through cn is a multiple of p squared, plus h of c1 through cn plus any multiple of p is also a multiple of p squared. Okay, so suppose that's the situation. And then that's what we say. That's when we say h is a multiple of p squared for mod p reasons at c1 through cn. So if that's true about h, that it's taking a multiple of p squared for mod p reasons, then the partial derivative of h with respect to, say, xn has to be a multiple of p. In fact, any partial derivative will have to be multiple of p, but we'll just do it with respect to the last variable. The partial derivative of h with respect to xn, evaluated again at c1 through cn, has to be multiple of p. That's the only way that something can be a multiple of p squared for mod p reasons. Any questions about the proposition? So if a polynomial takes a value multiple of p squared and takes a value that's multiple of p squared for every translate by a multiple of p of the argument, then that means that the partial derivative with respect to any of the variables has to be multiple of p at that argument. Okay, and why is that? Well, let's plug in just c1 through cn minus 1 and keep the last variable an indeterminate. So and then we'll expand that as a Taylor series around cn. We'll take the one variable polynomial h of c1 through cn minus 1, comma xn, and we'll write that one variable function as a Taylor series around cn. So first term is just evaluated at cn, and the next term is the first partial times h of c1 through cn times xn minus cn, and then their higher order terms in xn minus cn. Right, so that's just the formula for the Taylor series, and well, that's it. So now you look at this, we know that this is a multiple of p squared, and this is a multiple of p squared. So if we plug in something for xn that's congruent to cn mod p, then this will be a multiple of p squared, and we already know that this is a multiple of p squared. And so, yeah, so that means that this partial has to be a multiple of p, because this, remember, we're plugging in something. We're going to be plugging in something for xn that's congruent to cn mod p. Right? So we know that this is a multiple of p. We know this is a multiple of p squared. We knew this is already a multiple of p squared by hypothesis. And so therefore this partial at cn also has to be multiple of p for this term to be a multiple of p squared. So that proves that the partial evaluated at cn has to be multiple of p. Okay, so that's the proposition that we can apply in our situation. In our situation, we have a discriminant of a polynomial that's a multiple of p squared for mod p reasons, and therefore, if you take the derivative, partial derivative of the discriminant function, right, that has to be a multiple of p for our polynomial. If the discriminant of the polynomial is a multiple of p squared for mod p reasons. So in particular, if we take the discriminant of f, we're assuming f is a multiple, right, has discriminant of multiple p squared for mod p reasons. Therefore, the derivative, right, of f, we're going to treat the discriminant of f as a polynomial in the coefficients of f, right? And we know that it's taking a value that's multiple of p squared for mod p reasons. And therefore, if you take its partial with respect to, say, the last coefficient an, right, it'll have to be a multiple of p. Okay, so if f has the property that its partial is a multiple of p, then if you take, and we know that the discriminant of f, right? So the discriminant of f is a multiple of p, and its partial is also a multiple of p. Therefore, the resultant of f and its partial derivative also has to be multiple of p. But that's just what's the resultant of a polynomial and its derivative? It's just the discriminant. So what we're saying is that if f of x had the property that its discriminant was a multiple of p squared for mod p reasons, then that means if you take the discriminant of f of x, and then you take its discriminant as a polynomial in an, that will be a multiple of p. Okay, so we get that. So since f had discriminant of multiple of p squared for mod p reasons, that means its discriminant was a multiple of p, but also its partial with respect to any one of the variables, right? Say the last variable of f will be multiple of p, and therefore the resultant of the discriminant and its partial will be a multiple of p, and therefore the discriminant of the discriminant will be a multiple of p. So this is great because the discriminant of f of x, if you take the discriminant of that with respect to, say, an, the last variable of f, that polynomial does not involve the last variable. It doesn't involve an, right? So the discriminant with respect to an of the discriminant with respect to x of f of x does not involve x, but it also does not involve an. And we know it has to be multiple of p. If f had that property that its discriminant is a multiple of p squared for mod p reasons. So we produced a polynomial that doesn't involve an. That has to be multiple of p. That's very useful. So remember, we're considering the case where f of all f for which the product c of ramified primes is greater than h. So for such an f, the polynomial discriminant of a1 through an minus 1, right? So we call that dd. So dd of a1 through an minus 1 is just a polynomial that's the discriminant with respect to an, or the discriminant with respect to x, f of x. For such an f, polynomial dd of a1 through an minus 1 has to be multiple of c. Right? So if f has the property that its product of ramified primes is c and has Galois group that's not Sn and it's primitive, then we've concluded that there has to be this polynomial just in the first n minus 1 coefficients of f that is a multiple of c. It doesn't involve an. Now the number of possible a1 through an minus 1 for which dd of a1 through an minus 1 is 0. By the way, you do have to check that this dd of a1 through an minus 1 doesn't vanish identically. That would be a lame reason for it to be multiple. But in fact, it doesn't. It's an actual polynomial. It's not too practicing. So it's polynomial of a1 through an minus 1, non-trivial. And the number of a1 through an minus 1 for which dd of a1 through an minus 1 is 0 is at most big O of h to the n minus 2, right? Because it's one non-trivial polynomial condition. Total number of values for a1 through n minus 1 is h to the n minus 1, but if you impose this non-trivial condition, then it's most big O of h to the n minus 2. And then the total number of values for an, once you fixed a1 through n minus 1, big O of h to the n minus 1, because there are h possible values for an. So we've just disposed of the case where dd is identically 0. Number of such polynomials f for which dd is identically 0 is at most h to the n minus 1. So that's good. We don't have to worry about that. So we can assume that we have a1 through an minus 1 for which dd of a1 through an minus 1 is non-zero. Okay. So let's fix a1 through an minus 1 since the dd of a1 through an minus 1 is non-zero. Some fixed polynomial a1 through an minus 1. Then we know, since it's non-zero, it factors and it has the most big O of h to the epsilon factors. C bigger than h. We're in the case where c is bigger than h. dd will have the most big O of h to the epsilon factors. C bigger than h. And once C is determined, so let's fix A1 through A minus 1, that determines C, right, up to h to the epsilon factors. That determines C up to h to the epsilon values. Right? So once C is determined by A1 through A minus 1, then we know that, right, the discriminant is vanishing modulo C. Right? So the discriminant is a function of A1 through AN, and it's vanishing modulo C. So AN satisfies the polynomial equation, meaning the discriminant is coming to 0 modulo C. Once you have A1 through AN minus 1, then so once you have A1 through AN minus 1, then C is determined, all right, up to h to the epsilon possibilities. And then AN is determined because AN satisfies a polynomial, namely the discriminant, modulo C. And so you can solve for AN. So then the number of solutions for AN modulo C to this equation, discriminant of f is 0 mod C, is clearly just the degree of the discriminant polynomial. You have to do it for each prime dividing C, so that's why you have to raise it to the omega of C. But for each prime dividing C, AN is determined, and then by the Chinese remainder theorem, AN is determined actually modulo C. So this discriminant to the omega C is also most h to the epsilon size. And since C is at least h, the number of AN, okay, so AN is determined modulo C, but since C is bigger than h, AN is actually determined, right? Because AN has to be between minus h and h. That's where we're using the fact that C is bigger than h, because we've determined AN modulo C, but h is much smaller than C, so if it's determined modulo C, it's actually determined. Okay, so that means the number of AN is also at most h to the epsilon once A1 through AN minus 1 are fixed. So just to summarize the argument, once you fix A1 through AN minus 1, if dd vanishes on them, then we know it's a small order of magnitude anyway. And if dd doesn't vanish on them, then it has a bounded number of factors. C is determined by A1 through AN minus 1, and therefore AN is determined because AN satisfies the polynomial equation, namely discriminant to 0 modulo C. AN is determined modulo C, and since C is bigger than h, AN is actually determined because it's determined modulo C. And so the total number of f in this case is again, at most, big O of h to the n minus 1, because the total number of values for A1 through AN minus 1 is at most h to the n minus 1. That determines C, and then that determines AN. So it's needed to fix A1 through AN minus 1. Okay, so that gives big O of h to the n minus 1 plus epsilon. We had a bunch of h to the epsilons around, and that's why we don't get big O of h to the n minus 1 here. We get h to the n minus 1 plus epsilon. Okay, that was the harder part of the argument. Any questions on that? That's not too bad. Okay, so I'm going to maybe address the question of how to get rid of all these epsilons, right? Remember, the C was determined up to O of h to the epsilon factors, right? Because C is a factor of dd, and dd can have h to the epsilon different factors, and we have to sum over all possible C's that could come up there. So that's an h to the epsilon. And then here also, when you're solving for AN, using the equation discriminant of f is 0 mod C, C has many prime factors. If you fix A1 through AN minus 1, AN is satisfying some polynomial modulo C, but if C has many prime factors, that could still have lots of solutions in terms of the number of prime factors in C. Right, the number of solutions to a polynomial equation mod C, if the degree is n, is n to the omega C, right, n to the number of factors of C. So there are a number of places where it's h to the epsilon came up. How can we get rid of this? So until now, this was the last case, right? So we have proven at this point that the number of such polynomials is big O of h to the n minus 1 plus epsilon. And so now So that's what we've proven until this point. The n of h is the number of monic integer polynomials of height of h, whose Galois group is lat Sn, and the number of such things is the most big O of h to the n minus 1 plus epsilon. And the question is, can we remove the epsilon? And yeah, as I said, this is as much work as the rest. It's just getting to n minus 1 plus epsilon. So we have it, first of all, we have an epsilon in case 1 already. So in case 1, remember we had an epsilon. Now the reason being that if you sort of sum, we already have this r to the omega d coming up with the density, so that's an epsilon. But you can see that if you summed d bigger than, say, h to the 2 plus something positive, then you could subtract that exponent here. Right? If you're only summing, if you do d bigger than h squared, that's what results in the saving just one exponent here. But if we're going to do d is greater than h to the 2 plus 2 delta, if you just increase this exponent just a little bit, then the sum is a little bit less by a little power. So we're just going to change this case by saying d is bigger than h to the 2 plus 2 delta, and then that'll get rid of that epsilon. That's how we get rid of that epsilon. Okay. So to remove the epsilon in case 1, we replace the condition c less than or equal to h and d greater than h squared by just c less than or equal to 1 plus delta and d greater than h to the 2 plus 2 delta for some small delta given 0. Now there's an issue here that if you replace c less than or equal to h by c less than or equal to h to the 1 plus delta, remember how we did this? First case was just we imposed conditions modulo c, right? And since c was less than or equal to h, which is the size of the box, we were good. But if c gets a little bigger than h, say it gets the size h to the 1 plus delta, then we're in trouble, right? Because our box length is h, and we're imposing conditions modulo c, which is a little bit bigger than h. So how do we handle that? We want to know that even though c is a little bit bigger than h, we can still say that the number of congruence classes modulo c that we were counting, that density is sort of the correct density, even though the box size is smaller than c. And for that, if you just have a little bit of equidistribution, right, of the points that you're counting, then you can just get the same estimate. So we have to go in and try to prove some kind of equidistribution, because the conditions are now modulo number c that's potentially bigger than the side length h of the box. So what we use some Fourier analysis modulo c so we bound pointwise the size of the Fourier transform of the characteristic function of the set modulo c that we're counting. And it turns out that has a lot of cancellation because the kind of condition that it is about having multiple roots modulo c. There's a lot of cancellation in the Fourier transform, and then using Poisson summation, because you have a good bound, lots of cancellation in the Fourier transform. By Poisson summation, you have a lot of cancellation in the original sum. So that proves an equidistribution result about that set that we were trying to count modulo c, namely those that have lots of multiple roots modulo c. And that allows us to extend the validity of the count even when c is a little bit bigger than h, because we know that the set we're counting is equidistributed well enough that even if the box is a little bit bigger, I mean, even if c is a little bit bigger than the size of the box, it's still true that the number of points in there is the total count times the density.
So I'm a bit confused. Why did you have to modify in your cases the size that c is allowed to go up to? Why couldn't you just change, run the Schmidt argument for small d to d smaller than 2 plus delta, and then modify only the, Yeah,
you're right. For case 1 to remove the epsilon, you only needed the h bigger than, you only needed the d bigger than h to the 2 plus 2 delta there. But I also threw in, there was a reason why, well, again, this is the condition where c is less than or equal to h to the 1 plus delta. I'm going to need that c is bigger than h to the 1 plus delta in the new argument in case 3.
Okay, yep, thanks.
Yeah, be right. Yeah, this part, yeah, this assumption is not needed to save the epsilon in case 1, but we needed to cover it so that we can replace case 3 by c bigger than h. Yeah, good question. Okay, what about case 2? Well, remember in case 2, so in case 2, we're just going to replace d is less than or equal to h to the 2 plus 2 delta. So that therefore there's strictly more polynomials now, right? But remember we already had a power saving in case 2. So delta is small enough, we'll still have a power saving in case 2. So that's fine. And since we already had a power saving there, this case is still we go of h to the n minus 1. And so what remains then is just case 3. And case 3, as Lynn just asked, that's just going to be c bigger than h to the 1 plus delta n, because we've handled c less than h to the 1 plus delta n by Fourier analysis. Okay, so case 3 has now been replaced by c bigger than h to the 1 plus delta, and this is a strictly smaller case now, so we have a chance of getting rid of the epsilon. And so how will we do that? So remember how that case worked? We looked at dd, this auxiliary polynomial that was the discriminant of the discriminant of f, and we looked at the number of factors of it, right? And there are two sources where epsilon came up in case 3. The first was that we were looking at the number of factors of dd of a1 through a minus 1. That was h to the epsilon. And the second place that it came up was that once we fix a1 through an minus 1 and we fix c, we solve for an modulo c using the equation discriminant is 0 mod c. And because c could have many factors, we found that the total number of polynomials is again exponential at n minus 1 to the omega c. And that was the other choice of the h to the epsilon. So it's mainly when there are lots of ramified primes in c that's kind of problematic. And that's when we solve these h to the epsilons around. And so yeah, there's this trick that you can use to remove all these epsilons. It's really fun to find. To remove the epsilons in these arguments, we choose a suitable factor c prime of c. So c prime is just some subset of the ramified primes being multiplied together. And we find a suitable factor c prime of c that's between h to the 1 plus delta over 2 and h to the 1 plus delta in size. And because that factor c prime is within this range, it's within the range where we apply Fourier analysis to get equidistribution. And so we can actually just, instead of using c, we can use c prime, and we can run the argument of case 1. And because c prime is in this range, we're just imposing congruence conditions about c prime, and we know how to count that because of our equidistribution result for boxes that are slightly bigger than h. So we'll just impose congruence conditions on c prime instead of c, but otherwise we can just do the same argument of case 1, just impose the congruence conditions of having multiple roots modulo c. And so in that case, we can just handle it by a method analogous to case 1 with c prime in place of c. Okay, and suppose such a c prime doesn't exist, where that's a factor of c between these two bounds, h to the 1 plus delta over 2 and h to the 1 plus delta. In that case, we can choose a factor c prime that's bigger than h of c, with the property that all the prime factors of c prime are bigger than the h to the delta over 2 in size. So you can think about it, either c prime will exist in the first paragraph, or the c prime property of the second paragraph will exist.
Can you say why you can't take c prime with c in the second case?
Oh, because all its divisors may not be bigger than h to the delta over 2. We're going to use that. So we want, in the first case, we wanted a c prime that's strictly between those two bounds, because then we can use the Fourier analysis argument, the equidistribution argument. Because you can only get equidistribution with just a little bit more size of h. If there isn't such a c prime, then it turns out there's always going to be a c prime that's a factor of c that's bigger than h in size, and all of whose divisors are bigger than h to the delta over 2. In other words, all of its divisors are bounded below. And if we have a factor c prime like that, that's bigger than h, and all its divisors are bounded below, then in that case, we can use c prime in place of c and apply the argument of case 3. Remember, case 3 before was just the case that c is bigger than h. Well, now we have a c prime bigger than h. Now that's the divisor. If we just do the same argument with c prime in place of c, and we'll still get a saving. But because c prime has the most bounded number of prime factors, so all its divisors are bounded below. right? So it has a bounded number of prime factors. We'll lose all the epsilons in here. So if there is a C prime divisor that's either between these two values, we can apply case 1. And if we have a C prime, all of whose divisors, well, that's bigger than H, factor of C, all of whose divisors are bounded below, then we can apply case 3, but we'll lose all the epsilons here too, because C prime has a bounded number of prime factors. And epsilons will come in because we didn't know any bounded number of prime factors. Okay, now why is there always a divisor C prime of either the first kind or the second kind of C? Well, you can just write C as a product of primes in increasing order, and just take a product of consecutive primes from the beginning. Okay. And at some point, we'll end up in between these two. And if we don't, that means we jumped over it. And that means all the primes from that point onwards are at least h to the delta over 2 in size. And they are forever after that. And because we started off less than this, and we end up more than this, all the primes from that point onwards will be more than h in size when we multiply them, and they're all going to be bounded below from h to delta over 2. So one or the other kind of C prime will definitely exist. Either the initial segment when you're multiplying, or that final segment. One or the other will be your C prime. In the first case, you apply case 1. In the second case, you apply case 3. And so that gets rid of all the epsilon.
Is that last paragraph the only place where you don't get a power savings?
Yeah. Over at h to the n minus 1?
Yeah.
That's exactly. Okay, so that proves Van der Waerden's conjecture. En of h is at most h to the n minus 1 in size, so that even without the epsilon. But there's some related results. Maybe I'm out of time, and I said that's all I'm going to prove. So maybe I'll just stop here. Thanks so much. Flash the slide.
So do you know anything about the constant in front of the big O? Big O of h to the n minus 1.
Oh,
Like a million, or is it a function of n? What function is it?
yeah, I could work it out in terms of n. It grows with n.
But is
The way
it astronomically growing with n?
Yeah, it goes exponentially with n at the moment. But maybe with some more to be better. And I didn't use that. Yeah, this is working so hard on the epsilon.
When the discriminant, your discriminant was the discriminant of the field or the polynomial?
Discriminant of the field. D was the discriminant of the field. Okay. Yeah. Q bracket x minus x. Yeah. And C was the product of ramified primes in that field.
Okay.
So this is what a permutation group having a linear factor means. This came up in an earlier question.
Oh. I mean, it's intransitive, but it has a fixed point.
Having a fixed point is what
Having a
having
fixed
a
point
linear
means
factor.
linear factor.
Okay.
Does this DD polynomial come up anywhere else?
Yeah, I've never seen it before.
Never
It's
seen it
very
before.
useful.
Okay.
Yeah. Discriminant and discriminant. I've seen some literature in the algebraic geometry literature on double discriminants, but they never consider this particular double discriminant of just a simple polynomial. There is a whole theory of double discriminants due to Callum.
Is there a similarity between the statistics for polynomials, like the one for number fields or Galois or
Can you repeat that? Sorry.
Is there a similarity for the statistics for polynomials in the end, like in this slide?
Yeah.
And
And number fields.
number fields or algebra?
Right. Yeah, it's quite different. Because you can have many polynomials corresponding to the same algebra. And because of that, the statistics behave quite differently. But the difference is exactly understanding polynomials corresponding to the same algebra. That's a very hard question. For example, we don't know if you you take a ring of integers in a number field, is there a monic polynomial since the z bracket x modulo that polynomial is that ring of integers? Yeah, at least. Yeah, we don't know. But most of the time there isn't. So that makes the set of polynomials and the set of fields very, very different. Isomorphism classes of fields and polynomials are very different behavior.
Assuming like as much for degree much bigger than h, should it be out? Is it possible to answer just 1 below 1 times h to the n minus 1, or are there some examples that I'm missing? Like assume n is much bigger than h, so 1 being a root is really uncommon, right? Because,
wait, are you comparing n and h?
I'm saying like assuming degree is much bigger than h, which is what you're assuming, right? Oh, you're assuming
We're
h.
fixing n.
Okay,
H go too far.
Oh, okay. So then the answer is like there's a lower bound of something like a little buffer or something, right?
Yeah. And maybe I'll just say, just for large n, actually, if you assume the g is not Sn or An, then you can actually, so if you assume g is not Sn or An and primitive, so once n is at least 10, you can actually prove big O of h to the n minus 2, so you can start to get even bigger savings off of n minus 1. I think that's related to it. And then if n is at least 28, you can actually save off 3. And for sufficiently large, here's how much you can save from using these arguments. So it's h to the n minus constant times n over a large squared n. So it's something that, so the amount you're saving grows with n arbitrarily. It becomes arbitrarily large. So you get arbitrarily large savings with n large. And the other things that these techniques do is give the best known bounds for given Galois groups, as I was saying. So for example, G being the cyclic group, you find the number of polynomials of height of most h is the most big O of h squared. So constant. It's independent in that case. This is just a joke. I mean, it's true that it's M11 is somehow the test case in all papers about this, starting with Serre and Dickros and Joe Buehler. So anyway, if you work in this area, you have to, by obligation, work out what your technique is for M11. So anyway, the best known was 10.5, right? Just half off of 11. It's the large certificates. The time we get 8.6. It's quite a bit less than those previously. 5, 6. And then finally, there's this question of Serre, where whenever he tries to Van der Waerden's conjecture, Serre always writes, oh, well, Van der Waerden's conjecture is about the case of the Weil group with An, that's Sn. But what if you look at the families of polynomials that whose generic Galois groups are other Weil groups? So here's one for Wdn, right? So if you just have coefficients, every other one being 0, then the generic Galois group of that is Weil group of Bn. And in that case, you can ask, well, how many don't achieve that generic Galois group Weil group of Bn? And in that case, these same techniques actually give you the asymptotics on the nose. Actually, on the nose, in this case, I can actually do the constant. H to the n minus 1/2 is actually the correct answer in this case. It's actually asymptotic h to the n minus 1/2. And if you ask for which one is not even the Galois group of Wdn, then you get the exact answer. That's h to the n minus 1. So these related questions of Serre also problems can be handled using the same techniques.
Well, how does this last thing go?
The very last one?
Yeah.
I mean, so basically, we're interested, if it's going to be one of these two Galois groups, then if you just contract this polynomial and just make this x to the n plus x to the n, right, a1 x to the n minus 1 and so on, that has to have Galois group Sn. So it's kind of reducing to the previous case. And then there's just a little bit of additional analysis to see whether you end up in this case or this case. To show, to end up in the case Wdn, this has to be a square. And that's what leads to this half here. And then if it is definitely a square, and you assume that, then what remains is just what comes from that.
Is there some polynomial whose generic Galois group is about group E8?
Oh, there are. That's much harder to describe. My favorite question at the moment is for WE6, which is if you take a cubic surface, you look at the 27 lines on the cubic surface, right? They're a generic Galois group is WB6. And so if you take the generic cubic surface, it's Galois group defined in that way, namely it's Galois group of the 27 lines. It should be WB6. By the large sieve, you can save off half an exponent of the coefficients of the cubic surface. Can you do better? It's an open question. I think that's the
G2?
next natural one to try.
What about G2? You get G2 in this.
Yeah, G2. The wild group of G2 is not so exciting.
It's not, you know, it's just D6, right?
Yeah. So,
But I, yeah,
it's just
okay,
like,
yeah, fine.
it coincides with those three cases.
Sure, okay. Right.
Are there any questions?
Any Zoom questions? Perhaps not. So let's go on drill again.